Welcome to day 4 of the macOS and iOS Security Internet Advent Calendar. Today the topic will be the DILT shared cache, what it is and how it looks like. So when you look at any iDevice since iOS 3 or also on newer macOS, you will realize that all, or let's say nearly all, of the dynamic libraries have disappeared from the device. They're no longer found in the user lib directory. So the question is, where did they go? And what happened is that Apple took all the shared libraries and put them together into one big file. And this file is called the DILT shared cache. The idea behind this is not a security feature, it's more like a performance feature because you have to only map one file across all processes, and a lot of the initial setup work is done once basically and doesn't need to be done over and over again on every process start. So that's making it a bit faster. So when you look at the file system of iOS, you will find the different DILT shared cache files in system library caches apple DILT. Depending on what CPU is in your iOS device, there might be one or maybe more caches in there. When you look onto macOS, these files are basically stored in system library DILT. And here you usually have the ARM caches and the x86 caches for the emulation layer. And that's it. Loading of these caches is done by the dynamic linker with the help of special system calls in the kernel. And this file used to be mapped between 1.8 with a bunch of zeros and 1.9 with a bunch of Fs to this address space basically that was hard-coded. Nowadays it's kinda coming as information from the shared cache file, so they can kinda specify where they want to be loaded. When you look at these files, you will realize that they have a simple structure. This structure consists of 3 parts. First, you have the header part. Then you have the part that has the mapping data. And then you have the third part that contains metadata like code signing blobs, rebasing information, and so on. Within the header, you will find things like information about what mappings are contained in the mapping area, but also the list of all the libraries and a lot of other things that are part of the header basically. So the header used to be quite small, as you can see here. You see there's still a magic value in there, which is basically DILT underscore the version number, and then at the end of the 15 characters you will find the architecture of the target, and that's the magic. And then you have stuff in there like how many mappings do we have, how many images, that means how many libraries are in there, and where are these in the file, and you have information about the code signing blobs and information where the so-called slide info is. And slide info is basically the rebasing information in case you want to rebase, and because, for example, due to ASLR. So over the time, you will realize that this shared cache header grows and grows and grows because with every major version, Apple started to add more and more features to this shared cache file. Usually you can find the latest and greatest information about the header in this DILT underscore cache underscore format.h file. and you can find it always in the DILT source code that is released by Apple on opensourceapple.com. So you basically try to grab the newest DILT and you will find the newest header. So what changed here? The cache header got bigger because there's now something called branch pools and so on in there. What this means becomes clear later on. Okay. So again, with iOS 11, this was growing again and again. Now you can see there's some shared region start, shared region size, max slide. This is what I mentioned earlier. From this moment in time, the cache can basically tell the system, oh, I would like to be actually loaded into this address space here. And with the max slide, it can specify how much of ASLR the cache actually supports. So with iOS 12 and 13, the cache was growing again. Mostly stuff that is not really interesting to us unless you really want to parse everything on the lowest level. But as I said, it keeps growing and growing and growing. And with iOS 14, you are then in the situation that you have these new entries here that are called the mapping with slide offset and mapping with slide count. So we will see in a moment that basically since iOS 14, the cache has a few new features. And so the whole idea how mappings are defined inside the header has changed. And so instead of like redefining the original structures, Apple basically added a new mapping information at the end of the new header. And so that's basically it. By the way, if you wonder how these different cache headers get detected by code, usually the idea is that the code evaluates the mapping offset here. If that is of a certain length, then it knows, okay, we are in a newer version of the header, because these mapping definitions are usually directly after the header. So that's used as an indicator by the code usually what version of the cache we're dealing with. Okay, so now that was iOS 14, and with iOS 15 there's again new stuff added. And as I said, with every major version, Apple adds more and more features. And what you can see here now is they define something called sub-caches. And this is something we will go into in a moment. So let's go back to the mappings. I told you every cache defines the mappings inside the cache. And so they used to be defined via the structure. So basically, you used to have like 3 mappings in here. And so you have the address, the size, the address in the file, and then you have the protection level. And usually in the past, we had a cache that had like one mapping for a text segment, which was readable executable. We had one that was for data, which is read write. And then we had one for read-only data, which is read-only. That's basically the idea behind the mappings. And now, as I told you, since iOS 14, they have added some new features to this. And so now they basically have added the so-called slide info by mapping. So previously there was one giant slide info for all mappings, and now we have a slide info that is appended to the actually mapping. And also they have flags to define what kind of data is in the specific mapping, like auth data or dirty data or const data. So now back to these so-called sub-caches. So since iOS 15, the DILT cache is split into sub-caches. And the motivation by this is basically that the amount of libraries became so gigantic big that putting them all into one mapping becomes a problem, because you have things like relatively jumps and relative addressing, and they have certain limits on different platforms. And so this is one of the reasons why it makes sense to basically split one big mapping into smaller ones, because otherwise you cannot address certain things anymore, because the deltas become too big to be fit actually into the relative addressing opcodes. And so that's one of the reasons why now the big cache is split into sub-caches. How many sub-caches there are and everything is defined inside the header since iOS 15. And in addition to all the sub-caches that it defines, there's now an additional sub-cache added that is basically just a giant symbol file. And this is very handy for a reverser or security researcher, because it gives you a lot of symbols all over the libraries of the target system. But because all of this system and the subcaches and everything is new, there's actually a new system call in the kernel that can handle this. And that's just the system call is called shared region map and slide 2_np. And this is the one that the dynamic linker uses basically since iOS 15 to load this shared cache into memory. And then all the ASLR stuff and so on is automatically done inside kernel land. So we also had a definition of the images inside the file. So originally there were a reference from the beginning of the file. Since iOS 15 there's a secondary pointer to the images at the end of the header. And the definition is basically, it tells us where is this image in memory, what was the modification time on disk, what was the inode on disk, so you can identify what was the actual file. And then you have basically a string that is the name of the image. This is how it could look like. This here is just like extracted from an older file. I think it's even a 32-bit file, so you can just see this is the kind of information you would find in the image list. So now, as I told you earlier, at the end there's the metadata, and the metadata contains the code signing blobs, but also the slide info, which was the rebasing information. And there's like different version of this rebasing information, 1, 2, and 3. Nowadays, you will only see 2 and 3 used on 64-bit systems. 4 is for 32-bit systems, and 1 is a very old bitmap where they basically stored one bitmap per page inside the cache. But they wanted to have a faster and better version, and so they introduced number 2 and number 3. So the idea behind number 2 is that you basically store most of the information inside the unused bits of pointers. So basically for sliding, we only need to know, okay, this here is a pointer and we need to rebase it. And then we need to know where's the next one and the next one and the next one. And so instead of having like a bitmap of this as before, what we do now is we put basically the delta to the next pointer inside the unused bits of the pointer. So that means a part, usually the higher bits of the pointer, will tell you the delta, so where's the next pointer in the chain. And then the rest of the bits is basically the actual pointer value. And this allows us basically to encode chains of pointers, and the system can just traverse these chains and then rebase all the pointers. So in order for this to work, you need to have certain hooks, anchor points for the chains, because the delta might not be big enough to go to the next chain. So in this case, what this does is creates these page start offset and page start count. So that basically specifies where are all our beginning of the chains, and then how many of these chains are there. And then basically it's always a start from the chain and so on. This is important to know because it means ever since Apple introduced that, all the normal tools would break, because all the pointers that would see in the code would all have like trashed upper bits. And only if a program understands this, they can actually remove these dirty upper bits, basically. This is how this would look like in an IDA version that didn't just support this. You would see you have the pointer here in the lower bits, but the upper bits here is basically the delta, which is here 4. So I would know, okay, here's the next pointer. There's the delta is again 4. So it would go to the next pointer, and so on and so on. And yeah, so if your tool didn't know that, all of these things would not be recognized as a pointer, and so any disassembly would be broken. So how do you decode this? Luckily, this kind of algorithm that you need is basically defined inside the dilch cage format.h file that I mentioned earlier. So you will find code or pseudocode like this that tells you how to decode these version 2 slide info. So if your tool didn't understand this by default, you would have to write your own tool that basically pre-processes the whole cage and basically removes all the dirty bits from all the pointers. I have done this in the past, and in my longer form trainings, I usually give out the tool. But here, just let me tell you, the pseudocode is here, so it's kind of straightforward to write such a tool. So now, on newer systems, there's a new version used. This is version 3. So the idea here is it works very similar to version 2, but we have a new problem. We not only need like chains of pointers for rebasing, but we also need to support the whole concept of authenticated pointers. So the idea is that an authenticated pointer is protected by PAC. We learned on the third day what PAC is. Yeah, but now we need to tell the system when it loads this shared cache that certain pointers are actually plaintext pointers and other pointers are protected by PAC in a certain way. And we need to store this extra information somehow. Again, this new extra information is again a problem for all the tools that need to deal with it. And if they don't understand the version 3 format, we have the same problem again, corrupted pointers all over the shared cache in memory. So luckily, the dirt cage format.h also contains the format of these new pointers. And what you can see here is that it defines two different kinds of pointers. We have plain pointers and we have authenticated pointers. So for plain pointers, they basically use the lower 51 bits for the actual pointer value. And then these 11 bits are the offset to the next pointer. So that's the delta. And then we have a few unused bits here to make it the full 64-bit. For authenticated pointers, it's a little bit different. First of all, the highest bit is used as a toggle that tells us, oh, okay, this is actually a PAC protected pointer. Then the second one is also unused here from the top. And then the rest is all used. So the idea here now is that when we have a pointer that comes protected, it is a pointer usually inside the code itself, like inside the data, inside the code, inside the actual shared cache. And the shared cache is not that gigantic big. So we basically store the pointer as the offset from the shared cache base. We have 32 bits for that. So it's obviously up to 4 gigabytes away from the beginning of that specific shared cache, or whatever the base is used inside the shared cache, like the beginning of the mapping. So the rest here is a little bit harder to understand. So okay, offset to next pointer again is 11 bits for the delta. That's still the same, but now we have something called key, has address diversity and diversity data. So to understand this, you need to understand that the key is basically just selecting which of the 4 keys of pack is used, the IA, IB, DA, or DB. So inside the file, inside the information itself, you can say, oh, this pointer needs to be protected by this key, this pointer needs to be protected by this key. Now, some of the pointers also need to be protected with this context modifier thing. And here you can see why the official terminology from ARM is called modifier. Apple actually calls it the pointer diversity or address diversity. So basically, when the address diversity is set, then it will override the upper 16-bit of the address of a pointer with this what we called earlier the modifier, the diversity data. So again, we saw yesterday why we need that, because the pack uses this for the verification. But this here now shows you that when the shared cache is loaded, how the system ensures that basically all the pointers that need to be protected are actually protected. So we have the same problem here again. If our tool does not support this yet, we need to pre-process it with our own tools. Again, the algorithm for the desliding, or the basically fixing the content, is again inside the comments of this dirt cache format.h from Apple. So you can see the full decoding of the data. This here is the raw version, and this here is basically the pack version. And here it says sign blah blah blah, but if you just want to decode it, you would just ignore the signature. You don't need a signature, you would just use the plain pointer. Okay, so far for the sliding, but there was another problem since around, I think, iOS 10. And this is when you loaded this into a tool like IDA, you would actually see that all the calls here to library function would end up being broken. And the reason for this is that when you load the shared cache into IDA, you usually would have the option to load a single module or the whole cache. If you load the whole cache, you would end up in usually big problems, because the problem here is that the cache is so gigantic that your system will slow down dramatically unless you have a really powerful system with a lot of gigabytes of RAM. So let's say you don't have that, then you would usually just load a single module. So when you do that, you would end up with code like this, where the branches basically go to a red address, because that is the target address of the actual function that you would not know what the function is, and it's outside of your module. So In reality, it's even a bit worse because this is not necessarily actually a real target address. So why did this happen? This basically happened because for performance reasons, Apple would go through all the libraries to all the stub functions and basically remove the stub functions, or let's say it removes the calls to the stub function and goes to all of these calls and converts them into actual direct calls to the actual target function for performance reason. So ignore the whole step of the stub function, just go directly to the target. The problem here, however, is that sometimes that's not possible because the code is limited by what you can encode into an opcode. And there's only a certain distance that you can jump with a BL opcode. And for that, Apple created these so-called branch pools. So basically they use slack space inside the dual shared code, and when the target function is too far away, they actually find some slack space that is nearby, and then they branch to the slack space instead, and in the slack space they set up a branch to the actual target function. But sometimes that even is also not good enough. In this case, they would branch to the next one and the next one to the next one, and then maybe eventually they are near enough to basically branch directly to the target function. So you basically have these branch chains that finally go to the actual target. And of course that's a big problem for a disassembler that hasn't loaded all the cage into the system. Luckily nowadays Hexrace has a feature where you, when you have an unresolved function call here, you can then right-click on the specific target, and it will allow you in the drop-down box to basically load that specific module that defines this address. So you can basically ensure that the target module is loaded into your IDA library at the moment, and that allows you basically to have a better disassembly because it loads everything that it needs to understand the call directly. So you can see this is how it would look like these days after you have right-clicked it, so you would know where the target goes to and everything would be fine. So yeah, and let's go back to the new feature in iOS 15. I mentioned this earlier. So since iOS 15, there's actually an additional symbols file in addition to all the subcaches that might exist for your architecture. And this symbols file is very handy because it gives us direct access to all the symbols all over all the libraries that get loaded into the system. They get stored inside this structure here, and you have an nlist64 type. This is defined like this, and basically you then have information over all these symbols in all the images and so on and so on. This is very nice to understand basically when stuff crashes or so. You can very easily symbolize addresses inside the shared cache from this giant symbols file. And that's it for today. It was a pleasure having you again. See you tomorrow for day 5 of the Advents calendar.